Now then, let f of x equal the square root of x plus 3. Use the tangent line at x is equal to 1 to approximate, and then you can see a variety of function values here. Do your answers over or under approximate the value of the function? So here's the usefulness of this. And when we start talking about series in the very last chapter for all you BC students, we're going to refine this a little bit more and get an even better approximation than this tangent line approximation. But that's what it's about. It's about approximating a function like an irrational function or a transcendental function that is hard to evaluate by hand, especially in these trying times when we don't have a pocket calculator handy anyway. So let's say, for example, we're trying to find f of 1.1, which is equal to the square root of 0.1 plus 3, which is the square root of 4.1. Hey, what the heck is the square root of 4.1? I don't know. I know the square root of 4, but 4.1 without a calculator. So it's the idea of being able to get a pretty good approximation to the square root of 4.1, as we're going to see here, okay? All right, so we're going to start the whole thing by finding the equation of the tangent line. I need a point and I need a slope. Well, the point's pretty easy. So the point here, f of 1 is equal to the square root of 1 plus 3, square root of 4. Hey, we were just talking about the square root of 4. It's equal to 2. So I have my point 1 comma 2. Now, in order to find the slope, we're going to have to find the derivative. So f prime of x is equal to, and think of that, of course, as x plus 3 to the 1/2 power, which we will leapfrog down, x plus 3 to the negative 1/2 power. And then, hey, don't forget the chain rule. Got to multiply this by the derivative of the interior. If you don't, you miss the question. Times 1. All right, and then let's rewrite this to make it look pretty. 1 over 2 square root of 1, not 1 plus, how about x plus 3? There we go. And specifically, we needed to evaluate that at 1. So f prime of 1 is equal to 1 over 2 times the square root of, which we already found, 4, which is 2, which is 1/4. All right, so here's our slope. And, you know, I'm going to rewrite that because it was looking kind of weird. Anyway, so I've got my slope, I've got my point. I can write my local linear approximation, my tangent line, through these two values. So y minus 2 is equal to 1/4. There it goes again. My 4 looking ridiculous. X minus 1. Which, you know, under most circumstances, I can leave this tangent line exactly like this, box it up, and then go out for a sandwich or something. But in this particular case, we want to solve it for y because we're going to use it to approximate the value of the function at a whole bunch of different numbers. Those suckers right there. All right, so we're going to solve this thing for y is equal to, I got 1/4 x minus 1/4, and then I would add over the 2. 2 in terms of force would be 8 force, which is what, a total of 7 force. Okay, so our equation here is y is equal to 1/4 x, my force, they're not cooperating today, plus 7 force. Okay, so here's my tangent line, and I could say that my function f of x, which is equal to the square root of x plus 3, should be approximately equal to 1/4 x plus 7 force, at least around in a very, very small interval around x is equal to 1. So if you wanted to approximate this function at a different value, you'd probably want to switch your x equals 1 to something that would be a little bit closer. Okay. So just for the sake of this, I'm going to go ahead and evaluate one of these things. So let's say that, for example, I just did 2 because that one's going to be pretty easy. If I were to just plug into, this is f of 2 is equal to the square root of 2 plus 3, so 5. Scribble that out, put a 5 there. What's the square root of 5? I don't know, I don't remember. Calculator probably does. I don't. Anyway, is 1/4 times 2 plus 7/4, which is about, well, not even about, it's exactly 2/4 plus 7/4, which is 9/4. Well, there you go, as an approximation for the square root of 5. Now, to be quite honest with you, going out this far is probably not the best idea, but that was just the easiest one whenever I was looking at these numbers to plug in by hand. Here, let's take a look at a table of values, those things in particular, along with a graph. All right, so here then is a list of all the x values there, the ones that we wanted to approximate. And here are all of the local linear approximations for each of those, as well as the actual function value. Now, all of these function values are rounded to the nearest, 3 decimal places, because we do have an irrational number there. Well, except for that one. That one's not approximated. That's exact. Okay, so if you take a look, how close these two things are, right? They're indistinguishable, accurate to 3 decimal places. Same thing with this one, accurate to 3 decimal places. But then when we get to 1.5, which is only half away from the point that we started with, we're really not that far away. It's only starting to get further away, like we march away one more than our original x value. Here's a graph of it. So you can see that our green tangent line, which is approximating this function right over here, it is super close to that square root function. And so it's a great candidate to be able to approximate the function. Here, let me zoom in just a little bit more. Right? Very hard to detect the difference between those two things, between 1 and 2. Oh, why is that table up here again? Who knows? And then here you go. You can barely, you really zoom in, you can barely see the difference between the original function and the tangent function. Okay, so the last part of this question says, do your answers over or under approximate the value of the function? Well, if I go back to one of these pictures, especially this one right here, it's very easy to see that the tangent line is up above the function, so it should be over approximating it. However, most of the time, you don't have the original function, because if you did, what are you doing approximating the thing, right? So what we're going to do is figure out whether or not our original function is concave up or concave down, because that'll tell us where the tangent line is. If the tangent line's up above it, then it has to over approximate the function. And if the tangent line's above it, what kind of shape does this function have to be? It has to be concave down. So we're going to pick up that in the next video.